Thursday morning. So what we're going to do today is, well, continue with discussion of reabsorption of solutes. We're focusing on tubules. So we'll review sodium and glucose that we went through on Tuesday. We'll talk about glucose, urinary glucose in the setting of diabetes for just a few minutes. Then we'll transition to learning about the reabsorption of bicarbonate, which you know is important in how the kidney works with the lungs to control pH. And then we'll learn about potassium, which is complicated because it includes secretion as well as reabsorption. So potassium is complex. And then we'll start to talk about water reabsorption by the loop of Henry. We probably won't finish all these things. We'll continue on Tuesday with the water reabsorption. But I want to give you enough material to work on to finish the problem. So we'll quickly go through the sodium story. The sodium story includes, well, obviously sodium is filtered at the glomerulus. Then 2/3 of the sodium is reabsorbed in the proximal tubule. And that reabsorption of sodium is accompanied with reabsorption of water because the epithelium is leaking to water. So when solute is reabsorbed actively, water is reabsorbed passively because of water permeability. In the ascending limb of the loop of Henle, another 25% is reabsorbed. And this is sodium reabsorption without water reabsorption. This is going to become important for water homeostasis in a few minutes. So this is sodium recovery, but no permeability to water. And then in the distal tubule and the collecting tubule, the remaining 8% are reabsorbed. So that's the broad overview. And we went through these interesting pictures. Let's spend a few minutes going over this. So let's start with this picture. You point to a protein that is important for sodium reabsorption in this picture, and then tell me a little bit about that protein. What is it doing? One sentence. Yeah, reabsorption of sodium. Pick a protein and tell me what it's doing. Yes, that's the sodium glucose cotransporter. Okay, it's transporting sodium and glucose, but sodium from the tubular lumen, from the tubular fluid into the cytoplasm. That's all we need to know for now. Go ahead and pass the laser on. So this is an important one. We just described what it's doing. Yeah.
And it pumps sodium out to interstitial space.
Pumping sodium out of the cell into the interstitial space, lowering the sodium concentration in the cytosol, providing the sodium gradient for this process. This is the sodium proton exchanger. What's it doing for us here?
It's using the proton gradient to pump sodium from the lumen to the cell, and then that will get transported into the
Right. So sodium potassium ATPase is making the sodium gradient. This protein is harvesting or using the sodium gradient to move sodium down its concentration gradient, and We'll talk about protons later.
That's the sodium bicarbonate co-transporter, and it's taking sodium out into interstitial space and
So is this using the sodium gradient?
then,
No.
yeah.
What's this? This is pumping sodium.
Yeah,
Well, is it using ATP?
no,
No.
it's using the bicarbonate.
It's using the bicarbonate gradient to pump sodium out of the basal outer membrane into the interstitial space. So these are the kinds of concepts that you should know for sodium reabsorption. Okay, let's do the thick ascending limb. Who's got the laser? Okay. So some of the stories are the same, and you can retell the same story. That's the story that we want to tell. The sodium potassium ATPase. Go ahead, tell the story. Could be the same story that you just heard a minute ago. Let's reinforce. Yeah. Uses ATP, uses the energy from ATP. I'm just sort of embellishing a little bit, but what you said was right. Uses the energy from ATP to pump sodium out and to pump potassium in. But as far as sodium is concerned, to lower the sodium concentration in the cytoplasm. Did you intentionally skip Jasmine? Or?
I wasn't here on Tuesday.
Oh, okay. That's fine.
It also has the sodium proton.
Okay, we have this protein again, moving sodium in from the tubular fluid into the cytoplasm. Okay. Yes.
Did you say that was using the sodium gradient that's generated by the sodium potassium ATPase?
Yeah. This is sodium is flowing down its concentration gradient here, usually.
And the protein is just ballast the target.
The proton is the counter ion, and so this we are going to see this. We're going to use this for getting rid of protons when we want to excrete acid.
Oh, okay, so it works with
Yeah.
This is the sodium potassium chloride.
Okay, sodium potassium 2 chloride co-transporter.
And then brings sodium from
Okay, sodium is coming into the cell from the tubular fluid, and in fact, this is, depending on the concentration gradients, this can be purely passive or partially active. Let's not get bogged down in that. All right, I think those are the important proteins to talk about. Yeah. Let's not forget over here, in the early proximal tubule, in the proximal tubule, we have water. That's how it's a leaky epithelium right there. Okay, so you can see the stories. We don't have to go through any more detail. The concepts are, well, why not? Go ahead, Michelle. So now we're in the distal tubule.
So this is the sodium potassium ATPase that
So the potassium ATPase, what's it?
the gradient for the sodium to come from the sodium chloride co-transporter.
Okay, so you tell the whole story. This is creating the gradient, and this is using the gradient to move sodium into the cell using a co-transporter, a sodium chloride co-transporter, which is not the same protein as the sodium potassium 2 chloride co-transporters. Different proteins. Doing much the same thing, but two different proteins.
It's the sodium potassium ATPase,
Uh-huh.
which creates a sodium gradient.
Creates the sodium gradient, and why don't you go ahead and tell the whole story then?
So then when it draws it out of the cell to other channel.
Okay, so then sodium can flow down its concentration gradient through ENaC, the epithelial sodium channel, and as a result of sodium flowing down its concentration gradient, we have a pseudo exchange with a epithelial potassium channel. Sodium flows in, potassium flows out. Sodium is going down its concentration gradient, potassium is flowing out, down its electrical gradient, well, down its concentration gradient as well. But this is acting like an exchanger, except that it's not an exchanger. Okay, good. So these are the concepts that we'll be using to, to understand the molecular mechanisms of solute transport, of reabsorption in the renal tubules. Yeah.
So in all cases, the transporter, the sodium, the driving force.
The sodium potassium ATPase is what's driving this.
Oh no, I'm talking about like the sodium proton and sodium glucose co-transporter.
They're not driving, they're following.
So is the glucose that
Glucose
is
isn't.
stronger? Or
The sodium potassium ATPase is the driver. It's creating the gradient. And then, so the sodium potassium ATPase is creating the gradient for sodium, and then this transporter is using that gradient to move sodium in. Same thing here, except that now we're talking about the sodium glucose co-transporter. And in the case of glucose, this movement, which is driven by this pumping, is also driving this movement.
so they are all passive.
This is definitely not passive.
Yeah, that is not passive.
This may or may not be passive. This can be active. If the glucose concentration here is low and the glucose concentration here is high, this can happen and we would call it active. Active transported glucose, because it's using the sodium gradient to pump glucose. It depends on the concentration.
Bob,
Yeah.
if the sodium concentration is low in the lumen, then will this transport work at all?
If the sodium concentration here is lower than here, just doesn't happen. At least not in the proximal tubule. Okay, so here's the glucose story. 100% of the glucose is reabsorbed in the proximal tubule. If glucose is not fully reabsorbed in the proximal tubule, that is to say, if glucose gets here, it's going to get here, which means it's going to be in the urine, which is a diagnostic sign of diabetes mellitus. You may know that diabetes mellitus is high blood sugar. Let's talk about diabetes. Well, we'll talk about that in a minute. Ordinarily, the proximal tubule, the sodium potassium ATPase creates a sodium gradient. The sodium gradient is utilized by a sodium glucose co-transporter, SGLT, to pump glucose into the cell. And then glucose goes down its concentration gradient through a glucoprotein, glucose transporter. So SGLT, the thing you have to remember is S stands for sodium, sodium glucose co-transporter on the apical membrane, and then a passive glucose transporter in the basolateral membrane. Sodium is being pumped because ATP is being used, and glucose is being pumped because it's using the sodium gradient. In the early proximal tubule, the story is the same in the late proximal tubule. It's just that the mechanisms are a little bit more adapted for picking up those last few molecules of glucose so that we can get 100% reabsorption. That's the key. So this book went into detail about why SGLT1 is expressed late and SGLT2 is expressed early. It's just not a big deal. This is trying to explain why we can get every last molecule, practically, of glucose reabsorbed in the proximal tubule. Remembering, if we don't get it, every last molecule here, then it's going to go all the way out, and it's going to be in the urine. So let's do a quick. This is not a super easy one. Let's do it. While you're thinking about it, I need to fix my answer. Myself confused. Show me your answers. Okay, I'm seeing a lot of partial, some full correct answers. They're all correct. Let's go through them. The reabsorption of glucose depends partially on the activity of the sodium-potassium ATPase. Yeah, that's true. We need the sodium-potassium ATPase to build the sodium gradient, which is used by the SGLT to pump glucose in the apical membrane. The reabsorption of glucose depends on both secondary active transporters and passive transporters. Yes, SGLT is a secondary active transporter, and GLUT is a passive transporter. Apical membrane, SGLT to SGLT is secondary active, and basolateral GLUT proteins are passive. At the end of the proximal tubule, the concentration of glucose in the tubular fluid is lower than in the plasma of peritubular capillaries. Well, this is a normal person. The concentration at the end of the proximal tubule of glucose is 0. It's impossible to be less than 0, so that's no matter how, yes, that's true. Make sense? Inhibiting glucose reabsorption in the proximal tubule would increase glucose clearance. What is normal glucose clearance? 0, because we reabsorb every bit of it. So if we inhibited glucose reabsorption, then some of it is going to get in the urine, and it would increase glucose clearance from 0 to something. Okay, so that's why those are all true. So let's talk about diabetes for just a minute, because it's an important problem. So diabetes mellitus is a situation, it's an endocrine homeostasis problem that usually results in high blood glucose. And high blood glucose is bad for you because it increases blood pressure, it causes hardening of the arteries, it can lead to all kinds of cardiovascular problems, including bad circulation, which can cause limbs to have to be amputated, etc. So let's look at these data from another textbook, not from your textbook. So this is the plasma glucose concentration in milligrams per deciliter. Does anyone happen to know what a normal value for a fasting glucose concentration in blood is? You know, when they test for diabetes, what are they? When they do a blood test for blood sugar, blood glucose, what value are they? Is a normal? Anybody have a sense? About 100. Yep, about 100 milligrams per deciliter is a normal fasting glucose. It goes up after a meal, and it goes down when you fast. 100. So this is the normal. The normal value is here. Okay, so this is plasma glucose concentration in mg per deciliter. This is looking at either the filtered load, which you're going to work with on the problem set, or the reabsorption in milligrams per minute, or the excretion of glucose. So there's three different things being plotted here. So this is the filtered load. As the plasma, remember, filtered load of glucose is equal to the GFR times the plasma concentration of glucose. So as it's linearly filtered load, if we have a constant GFR, which we're assuming here, as the plasma concentration of glucose goes up, the filtered load goes up. So that's the orange line. Yeah?
Are you going to want us to be able to read this graph? We don't have it in our notes.
No.
No? Okay.
This is for your interest.
Okay.
You should be able to read a graph like this,
Right.
but I won't give you this graph and ask you to interpret. Filtered load. Reabsorption. Here's the point. Remember, the proximal tubule is the only part of the nephron that reabsorbs glucose. If the glucose gets past the proximal tubule, it gets to the urine. And the point is, the proximal tubule has a limited capacity. It's got a limited length, and it's got a limited expression of the GLUT transporters as well as the SGLT transporters. It's got a limitation. It can't pump all the glucose if the glucose concentration in the tubule is too high. So if the concentration of glucose in the blood plasma gets up to about 250, if the plasma concentration of glucose gets too high, the filtered load of glucose gets so high that the proximal tubule is overloaded, and now we reach the maximum. This is the maximum reabsorption of the proximal tubule. The proximal tubule can reabsorb up to, say, 400 milligrams per minute of glucose. And after that, it starts to excrete it. The main point here is that the proximal tubule is limited. It's got a limited length, and it's got a certain fixed number of transporters. And high blood glucose ends up in the urine as a sign of diabetes when blood glucose gets above, say, 250 milligrams per deciliter. Glucose is spilling over, that's actually the clinical term, spilling over into the tubular fluid that's leaving the proximal tubule, and it ends up in the urine. Zoe?
So when people have diabetes, one of the symptoms is like they pee more often?
Yeah.
Is that because of this glucose?
That's right. More
overload?
solute in the urinary fluid. We're going to talk about more solute in the urinary fluid means more water in the urinary fluid, which means more urine. More solute and more water is more urine, and that means they have polyuria. Polyuria means they're urinating a lot. And polyuria is usually accompanied by polydipsia. I'm just showing off now. Does anyone know what polydipsia might mean? If you have polyuria, what response might you do that would cause polydipsia? drink a lot. Polydipsia is drinking. Okay. Let's do another clicker. Yes?
So does that mean like people with diabetes are like more easily dehydrated because there's more water going into the
That's not the worst of their problems.
Right.
Okay, I'm seeing a lot of fully correct answers. B and D are correct. Let's go through them. In a normal person, the clearance of sodium is less than the clearance of glucose. No, in a normal person, the clearance of glucose is 0, and the clearance of sodium is some small number. A small number is bigger than 0. That's not a true statement. The reabsorption of glucose by the proximal tubule depends on the presence of sodium in the tubular fluid. Yeah, SGLT. Excessive reabsorption of glucose causes the clearance of glucose to be greater than 0. No, it's excessive filtration of glucose causes the clearance of glucose to be greater than 0, not excessive reabsorption. And D, glucose is freely filtered by the glomerulus, so high plasma concentrations of glucose cause high concentrations of glucose entering the proximal tubule. Yeah, that's what we just said. Okay, questions about sodium and glucose, about these mechanisms. You're going to be using some of this, use it in the problem set. Calculating clearance, calculating filtered load, calculating excreted load, comparing the numbers. I just want to say that the numbers were chosen to represent normal. So if you get a number that is way abnormal, check your arithmetic, because I want you to be seeing normal numbers and understanding why those numbers are normal.
So, we have to differentiate between the passive transporter versus the secondary active transporter.
Yeah. Passive transporter. This is passive, and this is secondary active. Question?
No, because it all comes back to the first slide when you show a lot of passive co-transporter.
Most of those co-transporters are secondary active. A co-transporter is almost always secondary active co-transporter. Sometimes a secondary active co-transporter can function in a passive mode, but they are all capable of doing secondary active transport, so we call them secondary active transporters. A passive transporter is incapable of doing any kind of active transport, and so it's passive. Remember, a primary active transporter uses ATP to pump solute. A secondary active transporter uses the sodium gradient to pump something else. And a passive transporter is always allowing something to flow down its electrochemical gradient. Question?
Could you come back to the clicker that you just used?
Go back to what?
The clicker.
The clicker that we just had?
For answer B, what do you mean by tubular fluid? Is that like the fluid in?
Tubular fluid is urinary fluid. The the fluid inside the tubules.
So it also contains of the fluid in the like
It also contains what?
of the fluid in the loop family and the distal.
Yeah, then we would call that tubular fluid. It's different, by the time it gets there, it's different tubular fluid, but it's not urine yet, so we don't call it urine.
But the reabsorption of glucose takes place in the proximal tubule, which
Right.
is like the very first tube.
Right.
So how could the presence of sodium in the next set of tubes contribute to the reabsorption?
Which one are we looking at, B? It won't. It's only the proximal tubule. But the question is, the reabsorption of glucose by the proximal tubule depends on the presence of sodium in the tubular fluid in the proximal tubule. It's understood
okay.
that it's the tubular fluid in the proximal tubule. I'm sorry, that was understood by me.
Thank you.
That, yeah. I guess I cut a corner there. That confused me. Is that clear now? Okay, let's talk about bicarbonate. Who's got the laser? Did you answer? You answered your question. Okay, me. You get to. So your book. This is from your textbook. Your book wants you to begin here, but I find it confusing to begin here. So I've cut and pasted a begin icon over to here. So we're going to begin here, and we're going to try to do these two things in parallel. It's a little complicated, but starting here gets me confused. How did this so we're going to start here. This is the tubular lumen. This is a cartoon of the epithelium. This is the interstitial fluid. This is a junction between, this is a epithelial cell. Here's another one. Here's another one, right? A whole cylinder of them. What's the name of the process, that brought this bicarbonate into the tubular lumen? And you can think of any section of the tubule, but maybe it's easiest to think about it in the very beginning of the proximal tubule. What's the name of the process? That's what I'm looking for in this box. That got bicarbonate into this fluid.
Is that or the bicarbonate should be transformed into the interstitial space.
Not over here, no, I'm in the tubular fluid.
Via the sodium bicarbonate or transformed.
Okay, but you're thinking over here, and I'm thinking over here, so that's not going to help us.
Maybe this
Diffusion. No,
Dissolve?
not exactly wrong. What's the word I'm looking for?
Dissolve?
Filtration. This is I think the word is filtered. Bicarbonate is an ion in blood plasma. It's small, so it is filtered. So bicarbonate enters the tubular fluid by filtration. Just the same way sodium and glucose did. Okay, so we're just going back to, remember, glomerular filtration happened, and bicarbonate is in the tubular fluid by filtration. Okay, now, how did this, well, water is everywhere. We're not going to worry about how the water got there. How did this carbon dioxide get into this cell? Han, have you got the laser? Well, now it's just a point. I'm not going to ask you to point to anything, because I'm going to point to things and you're going to explain it. So we don't need the laser right now. How did this carbon dioxide get into this cell? Diffusion. Where did it diffuse from? Me?
So from the blood plasma it goes
Okay.
into
From the blood plasma into the interstitial space, into the cell. There's carbon dioxide everywhere. In fact, there's carbon dioxide here in the tubular fluid as well.
Could it diffuse that way too?
It's going to diffuse down its concentration gradient. So it's going to diffuse in all directions. And so the point is, if the partial pressure of CO2 is 40 millimeters of mercury here, the partial pressure of CO2 is 40 millimeters of mercury here. That's because carbon dioxide is freely diffusible. It goes wherever it wants by passive diffusion. And since our lungs have, our body has produced CO2, and our lungs have exhaled some of it, a normal arterial PCO2 is 40, and so there's CO2 here. Okay, so now we've got bicarbonate here, and we've got CO2 here. Well, these cells express carbonic anhydrase. So they make carbonic acid from the CO2 in the water. In fact, most cells do, but these have a high expression of carbonic anhydrase. Carbonic acid dissociates into proton and bicarbonate ions. What should we? So this arrow is suggesting a process. Let's give it some more details. There are two proteins that do this. Who's next? Emily, can you think of, so we're in the basolateral membrane. There are two proteins that do this process that is cartooned here.
I don't know. Could it be like bicarbonate exchanger, or is that unless?
It could be, so, but there's another, what is the bicarbonate what exchanger?
Bicarbonate sodium, or no, chloride exchanger?
That's right, so that's one of the answers. We have a bicarbonate chloride exchanger. It's a secondary active transporter. And what's the other way that we move bicarbonate in the basolateral membrane? Anybody? Okay, not anybody. Who's next? Zoe. You don't know. Natalie.
Sodium bicarbonate.
The sodium bicarbonate co-transporter. The sodium bicarbonate co-transporter. You've seen these before. Where did you see these before? Let's just go back to this one. Remember, what we're seeing in the figure from your textbook is a generic version of a typical, any renal tubule. Well, there's the chloride bicarbonate exchanger, and there's the sodium bicarbonate co-transporter. So you've seen them before, and now we're just putting them in one cell. But that's an oversimplification. This book would say that's an oversimplification. Your book is a little bit simpler, so it's okay. Well, I gave you the answers. Okay, so sodium bicarbonate co-transport and sodium chloride exchange is what is embedded in this symbol. What's embedded in this symbol?
Are there two of them as well? Are there two of them as well?
Let me see.
Now it's in one.
Yes, there are. So let me put up the answer key. So what is embedded in that arrow? Remember, we're moving bicarbonate. What are we doing? I want to give you the answer. We're moving bicarbonate. I'm sorry, we're moving protons from the cellular cytoplasm into the tubular fluid. What are the names of the proteins that do that? The sodium proton exchanger, and something that's not shown. So it's an unfair question. The sodium proton exchanger is one answer. And there is a proton ATPase. That is the other answer. So they're both active. That's why we have this arrow pumping thing. That's a symbol for a pump. We have a sodium proton exchange. And we have a proton ATPase. That uses ATP to pump protons out. Okay? So I gave you this as something to fill in, right? So you've been filling in the details. And so out here in the tubular fluid, the urinary fluid, there's a process that looks familiar to you. What catalyzes this reaction? Carbonic anhydrase. So there is carbonic anhydrase in the cytoplasm, and there is a version of carbonic anhydrase that is actually anchored to the apical membrane. So this carbonic anhydrase is not soluble. You're not going to urinate it away. It's embedded in this membrane. So it's a carbonic anhydrase enzyme that has its enzymatic activity in the tubular fluid, but it's a membrane protein. So there's a soluble carbonic anhydrase in the cytoplasm, and there's an ectomembrane carbonic anhydrase. Why did I call it ecto? Because its function is outside the cell. And ecto carbonic anhydrase. Membrane bound. Okay, so now we've set up the situation. So can we explain the excretion of bicarbonate? Yes. Let's go through the story. Bicarbonate is filtered, and if it weren't reabsorbed, we would excrete too much bicarbonate. We want to conserve bicarbonate to keep our concentration of bicarbonate at around 26 millimolar. So we reabsorb bicarbonate. We need to reabsorb bicarbonate because if we filter it and get rid of it, our bicarbonate concentration is going to go too low. So we reabsorb bicarbonate not as bicarbonate but as CO2. Filtered bicarbonate is converted by the ectocarbonic anhydrase into CO2. CO2 diffuses. So the CO2, this CO2 becomes this CO2, right? This CO2 then becomes bicarbonate, which is pumped. Does that make sense? Remember, we're reabsorbing bicarbonate. Our goal, it's reabsorption. It's got an active component to it, but it's not as simple as sodium or glucose. Filtered bicarbonate, which we want to reabsorb, at least some of it, gets converted into CO2. CO2 gets broken down into bicarbonate in the cells, and the bicarbonate is reabsorbed. You're going to be using this in your homework. There's a homework problem addressing bicarbonate reabsorption. And you're going to be thinking about drugs that affect carbonic anhydrase and how they change bicarbonate excretion. Yes?
Did you say how much bicarbonate is reabsorbed too?
How much bicarbonate what?
Is reabsorbed? Like how much?
It depends. So I didn't say, And so it depends, remember, so bicarbonate reabsorption is controlled by the body's need to reabsorb bicarbonate. So let's remember, okay, let's remember the Davenport diagram. Concentration of bicarbonate, this is plasma. Concentration of bicarbonate with a typical value of around 26 millimolar. Typical blood pH, plasma pH of 7.4. Here's our normal value. If we hyperventilate, we want to excrete more bicarbonate. So we would upregulate we would upregulate bicarbonate excretion, which means downregulating bicarbonate reabsorption. So that's why there's not a fixed amount. It depends on what the lungs are doing.
So the kidney is not actually holding in the bicarbonate so much as choosing whether to excrete it or reabsorb it.
Exactly. Yes.
So it regulates that by carbonic anhydrous activity, or like how does it regulate that if once the CO2 exists in the tubular lumen, it's just going to get reabsorbed?
Right, so the things that are controlled by the body in order to, remember that in hypoventilation, we want to retain bicarbonate, right? So we can do it both ways. And the things that are regulated, up or down, are carbonic anhydrase, the expression of the exchanger, the expression of the exchanger. The amount of those proteins and how easy, so for example, well, I'm going to let you work through it because the problem set will help you work. I'll give you the answer to a problem set question if I go much further. Yeah.
Can the bicarbonate ion in the tubular lumen just like transcellularly?
Can they what?
Transcellularly.
No, we don't have transcell. We do not have a mechanism for moving bicarbonate across the apical membrane. The only way bicarbonate moves across this membrane is as CO2. CO2 can move wherever it wants, but bicarbonate can't. Okay, we can come, if we need to, we'll come back to this on Tuesday, after you've wrestled with it in the problem set. There's value to wrestling with information, coming to an answer. Okay, so let's do another clicker and then let's do a clicker and then we'll take a break. Most of you are choosing what is probably the better answer than I have up here, and I'm not going to take time to fix it. But they're all correct, right? Because the sodium-potassium ATPase is important for setting up the sodium gradient, which is important for the sodium bicarbonate cotransporter. So that would be a legitimate answer, but it's less direct. Maybe that's why I didn't choose it when I was answering my own question. Okay, so good. I think most of you got that. So the altitude sickness question I've converted into a problem set question, so we're not going to do this one as a clicker. So let's take a quick break, and we'll come back and do potassium. Potassium. So I can make this super hard, or I can make it because it's not easy. But let's go through it. I will not make it super hard. I will try to not make it super hard. So potassium is a solute that your body needs, right? The cytoplasmic concentration of potassium is high. You know that there are foods that are rich in potassium that you're told are good for you, like bananas. Let's go through the parts of the tubule where potassium is processed. So in the proximal tubule, there is significant reabsorption of potassium. Simple. So not quantitatively the same as sodium, but qualitatively similar to sodium. Potassium is reabsorbed in the proximal tubule. We'll talk about mechanisms in a minute. In the ascending limb of the loop of Henle, we got some reabsorption. Sort of like sodium. In the cortical collecting tubule, this is the difference. In the collecting tubule, remember this is the part right after the distal tubule, we have mechanisms for secretion of potassium. So this is the first time we've talked about a solute being secreted. Everything else has been either filtered or reabsorbed. Now we're talking about filtering and either reabsorption or secretion, depending on where we are in the tubule. And then in the medullary collecting duct, we got some reabsorption going on. So, depending on a lot of things, we can either excrete 10% of our filtered load. So this is excretion of, this is filtered load. If we excrete 10% of the filtered load, that means we reabsorbed 90% of it. Sort of like sodium, except that with sodium it's 99.5% of it. And it's sort of like glucose, except with glucose it's 100% of it. How can we excrete 150% of the filtered load? Secretion. We can both filter it at the glomerulus and secrete it in the cortical collecting tubule, so that what we excrete is actually more than what we filter because of secretion. If we maximize secretion, we can excrete more than we filter. Okay, so biologically, let's step back into the world of, let's get out of the kidney tubule for a minute and think about human beings on planet Earth, evolution. Why did we evolve mechanisms for reabsorbing 99.5% of our sodium, which is more or less constant? Really small variations. We reabsorb almost all of the sodium that we filter. But we have mechanisms for reabsorbing or secreting potassium. Why did we evolve that? Anybody have an idea? Okay, so potassium is really important for the resting membrane potential. Okay, so homeostasis of both sodium and potassium is very important, and yet we evolved mechanisms for reabsorption without secretion of sodium, and we evolved mechanisms for reabsorption and secretion of potassium.
Because you're not always doing the same amount of exercise, so you're not always doing the same amount of potassium?
Those are certainly true statements, but they're not answering the question.
Would it be like availability in diet, like sodium is a little bit more consistent, but.
A little bit more consistent. So let's think, is sodium readily available in our diet? It is now. Is sodium readily available before we started mining it out of the earth? Sodium is a rare thing in biology. You may have heard of a salt lick. Animals will flock to a salt lick in order to get the sodium that they so desperately need, but because they don't get it from eating grasses or from eating other animals. Sodium is a rare, out there in the world. I'm not talking about when you can open up a bag of chips and get 200% of your daily sodium requirement. I'm talking about, biology. Sodium is rare. And so we evolved mechanisms to conserve sodium. And now, in the modern world, this is a problem, because we need to be able to excrete sodium because we eat so damn much of it. But our body, evolution has not yet caught up with the food industry. Potassium is rich out there. Fruits, vegetables, seeds, nuts, meat are rich in potassium. And so in order to maintain homeostasis of potassium, we need to be able to either conserve it or to get rid of it in order to homeostase it. That's not the way to say it. In order to maintain homeostasis of potassium. Potassium is rich in our diet, in the evolutionary diet, and sodium is poor in our evolutionary diet, but not in our modern diet. So that's why we're here with thinking about secretion of potassium. Okay, so that's a concept that doesn't come easily to us because we think, oh, sodium, you just go buy a bag of chips and you get enough sodium. But, we didn't evolve in the bag of chips era. Okay, so here is a slide that I did get printed out for you. And this I could make super hard, but I'm going to resist. Let's talk about potassium reabsorption in the proximal tubule. Remember, 80% of this potassium that was filtered is reabsorbed in the proximal tubule. So let's try to understand that. Okay, what's going on over here? What's this? That's the sodium potassium ATPase. Which A is it pumping potassium? It's pumping it into the cells. So that's not going to help us reabsorb potassium. Right? Right there we got, whoa, that's complicated. But we've got this futile cycle. Potassium is pumped in and then leaks out through channels. Potassium is pumped in and then is transported out with a co-transporter. So there's just sort of this futile looping of potassium. As far as potassium is concerned, this is futile. As far as sodium is concerned, this is super important for building the sodium gradient. So this isn't a waste. It's just not going to help us understand potassium reabsorption because it's just a cycling of potassium. Okay, so if this isn't going to explain potassium reabsorption, what is? Remember, sodium reabsorption was followed by water flow. Remember, sodium reabsorption, it's a leaky epithelium. Water is flowing. Water is flowing with potassium. So we have paracellular reabsorption. Paracellular reabsorption of potassium. It's driven by the water flow, which is driven by the sodium flow in the proximal tubule. So you can see why it's harder than the sodium. Okay? So that's the key point. In the proximal tubule, potassium reabsorption is passive in the sense that it follows, well, no, it's not, yeah. It's passive in the sense that it follows sodium flow. Sodium flow is not passive, it's active because of the sodium potassium ATPase. So sodium is being pumped, water is following, and then water is dragging potassium with it. In a nutshell. Now you can say, well, why doesn't water drag sodium with it here? And it does a little bit, but the proteins that make up these junctions are slightly ion selective. And so potassium can move easily and sodium can't. That's not a testable fact. Okay, so there's sodium reabsorption. And now I'm just going, now we could, like I said, I could make this hard. But I don't want to. I want to get at potassium secretion. Where do we see a way to secrete potassium? And let's face it, we want to focus on the cortical collecting tubule, because that's where I said secretion happens. Well, here's the story of potassium secretion when needed. Potassium is pumped into the cell, sodium potassium ATPase, and potassium diffuses down its concentration gradients, not diffuses, either is transported passively or actively to pump potassium out in the cortical collecting tubule. And that's the story of secretion in the cortical collecting tubule. It's pretty straightforward. Potassium pumped by the ATPase, potassium flowing down its concentration gradient, either through a channel or through a co-transporter. So these are the important components of secretion in the cortical collecting tubule. Now, am I telling you the whole story of potassium? Obviously not, because there's lots of things we haven't circled. So, by the way, just as a point, here is that proton ATPase that I mentioned just a few minutes ago for proton extrusion by the apical membrane. So it does appear in one of these high quality images. It just didn't appear in the one that we had before. So what do you need to understand? You need to understand this process and this process for potassium reabsorption. And you need to understand this process for potassium secretion. And I think that'll be good enough. In your problem set, you will need to understand the interaction between those two processes. I mentioned this exchange mechanism. You'll see it when you get to the problem set. Okay, so, and if you have a question when you're wrestling with the problem set, please feel free to send me an email and I'll try to respond as quickly as I can. Due on Sunday. Let's do a clicker. Which of the following is important everywhere? All segments of the nephron for solute transport. Which of these proteins is present everywhere? Or which of these processes is present everywhere in the nephron? Give you a hint, there's one correct answer. Best answer is A. Paracellular, there are parts of the nephron. Remember, the ascending limb of the loop of Henle is not water permeable. So that one, B, is right out. Sodium potassium 2-chloride cotransporter is not expressed in the proximal tubule, but it is expressed in the ascending limb of the loop of Henle. That sort of thing. So only the sodium potassium ATPase is present everywhere. I mean, in all segments of the nephron. Why did humans, I think I already answered this question. Why did humans evolve molecular mechanisms for the reabsorption of sodium, but for reabsorption and secretion of potassium? There's one good answer. Let's just see if you were listening to me. Sodium is less abundant in food, normal food, than potassium. Okay, I'm gonna skip a couple of clickers. Well, no, I'm gonna do this one because it will help with the problem set. Because I'm gonna use some language that you'll need to know for the problem set. What is a diuretic? You're gonna be working with some drugs that are called diuretics. What does a diuretic drug do? Helps you excrete urine. Helps you produce and excrete more urine. So mannitol is called an osmotic diuretic. It increases urine production. That's what a diuretic means. Via an osmotic mechanism. Mannitol is freely filtered at the glomerulus, but is not reabsorbed. Which of the following is true? I'll give you a hint. There's more than one correct answer in this one. So is not appropriate. Which of the following are true? Hard because I didn't teach any of this. I'm just trying to see if you can figure it out. They're all true. So, why is A true? Somebody who chose A, explain why A is, well, I'll do it. It's freely filtered, but it is not reabsorbed or secreted. That's the definition of something that could be used to measure GFR. So mannitol could be used to measure GFR just the way inulin or creatinine could be. Mannitol is an osmotic diuretic because it is a solute that appears in urine. As something that is freely filtered but not reabsorbed or secreted, it appears in urine. It's a solute. So like glucose in the case of a diabetic, I think Zoe mentioned this, diabetics urinate more because they have glucose as a solute in their urine. And so remember that water follows solute osmotically. So if you have a lot of glucose in your urinary fluid, water is going to follow that and you're going to have polyuria. If you have a lot of mannitol in your even some mannitol in your urine, water is going to flow, and so that is going to make more urine, and that more urine making means it's a diuretic. So B is correct. Mannitol is not a substrate for the sodium glucose cotransporter, but if it were, we would reabsorb it. And I just said it's not reabsorbed. Mannitol does not follow a paracellular reabsorption path, same thing. If it went down its paracellular pathway, then it would be reabsorbed, and it's not. Okay, so that's how you can figure out that all of these were true. Okay, let's do another mannitol one. So this is now, again, helping you with the problem set. Most diuretic drugs, drugs that increase urine production, are used to increase sodium excretion. That's true of most diuretic drugs, the drugs that you're going to be working with on the problem set. Which is true of most diuretic drugs. Again, which are true. So more than one correct answer. A lot of you with all the correct answers. Since most of you got it, I'm gonna move on. John, do you have a
Can
question?
you explain the difference between excreted load and clearance one more time?
Mathematically,
Just like conceptually.
I'm not sure I can, I think I have to use arithmetic.
Okay.
The excreted load is equal to the GFR times the plasma concentration. No, I'm sorry, that's the filter load. The excreted load, start again, the excreted load is the production of urine, the rate of production of urine, that's a rate, mils per minute, times the urine concentration of that stuff. The clearance of something, so excreted load of something is the urinary fluid production times the concentration of that something in urine. The clearance of something is equal to so conceptually, clearance is excreted load divided by the plasma concentration. They go hand in hand. If something increases the excreted load, it probably increases the clearance.
So could you say that clearance is kind of a rate?
Clearance is a rate of fluid, it's a volume flow rate.
And then the excreted load is just the amount?
Excreted load is the amount per minute that is excreted. You'll see this in the problem set. You'll pay attention to the units. Okay, I'm gonna skip. So, I'm not too surprised that we didn't get to water. We'll start with water on Tuesday. I don't think you need water to do the problem set. Other than knowing that we have to conserve water, right? Remember, our glomerular filtration rate is 100 mils per minute of mostly water. If we don't reabsorb most of that, like 99% of it, we'll get dehydrated in a matter of minutes. I mean, literally, minutes, 5 minutes, and we would be severely dehydrated. We're not, because we reabsorb a lot of water. So on Tuesday, we'll talk about the molecular mechanisms of water reabsorption. We'll talk about sodium, potassium, glucose, bicarbonate. Now we're going to talk about water on Tuesday. I'll see you in lab this afternoon, and we'll look at some actual renal tubules.